Continuing with acids and bases, working again with Big Idea 6, we today are going to further explore Ka in regard to weak acids, Kb in regard to weak bases, a little bit with percent ionization, linking it back to Q, and then finally we'll talk about how to flip between Kas, Kbs, and the common ion effect. A lot of what we are doing today is very similar to what we did the other day, hence why you are going to need a mini quiz to make sure you understand some key concepts. Where we finished off last time was calculating Kb for a weak base when the concentration was given as well as the pH. And we weren't able to do the percent ionization concept, and that's what we're going to do now. And this will be the last piece of your mini quiz. With percent dissociation, also known as percent ionization, you're looking at the amount of acid that has dissociated in order to achieve equilibrium. If you have an acid, percent dissociation is proton concentration. That's going to be at equilibrium because you initially started with none. So proton or hydronium ion concentration at equilibrium over the initial acid concentration that was probably given times 100. If you have a base, it's grossly similar, but you're going to have hydroxide over the initial base concentration. So these types of problems can be very, very straightforward, where they may give you the initial concentration of a weak acid such as hydrofluoric acid and the proton concentration at equilibrium, and then to calculate percent ionization you just divide the two and multiply by 100. So there's not a lot to it, but more likely than not they'll give you a question such as this one, and this one we'll work through. It says, calculate the percent dissociation of acetic acid with a Ka of 1.8 times 10 to the negative 5 in a 0.1 molar solution. So in regard to what's given and what you want to know, we've got a Ka value of 1.8 times 10 to the negative 5. The concentration of acetic acid is 0.100 molar solution, and we want to know the percent dissociation. So here's the new piece of the puzzle. Percent dissociation is going to be hydronium ion concentration over the initial concentration of the acid times 100. Well, we have this piece, but we don't have the hydronium ion concentration. Can we get that from Ka and concentration? Sure we can. So this goes back to our rice table. You want to get in the habit of being very comfortable writing these equilibrium reactions, and again, if you're going after pH or pOH, you're going to be reacting the substance with water. You'll see later on in the chapter that you won't for other situations, but in these you do. Also remember that when you have a weak acid, you're going to generate hydronium ion. Note that this concentration will be less than this because it's a weak acid and it doesn't ionize completely. So you have 0.1 molar subtracting and this is all review. So Ka here is equal to, and this is exactly what I'm going to ask you to do on your mini quiz. I have it built into smaller sections so that I can award points as you go through. And the Ka is small. Actually, let me write it out as I did. I'll list both steps. Some of you probably don't need the first step, but in case they ask you for the acid ionization constant expression, I want you to be very comfortable with it. And again, the Ka is small. X is going to be less than 5% the molarity of the acid, and you can just ignore that. So if they ask you for the Ka expression, and I will, either Ka or Kb, you've got that right there. And from there, it's just a plug and chug situation. You've got Ka, which is 1.8 times 10 to the negative 5, times this, which is 0.100 molar, is equal to x squared. And the square root of 2 is 1.4. So the square root of 1.8, I'm going to guess, is 1.3 times 10 to the negative 3 molar is equal to x is equal to the hydronium ion concentration. Are you clear on that? That was from last time. And you did a lot of practice, so you're good to go. Yes, yes? Awesome. So percent dissociation then is going to be hydronium ion concentration over the initial concentration. And again, you can do this in your head as well. This is the same as this. That divided by that will be 1 times 10 to the negative 2 times 100. So you've got 1.3%. That's the percent dissociation.
You're dividing exponents, don't you subtract them?
Right. Negative 3 minus negative 1 is negative 2. 10 to the negative 2 times 100 is 1.
Oh, I thought you said negative 4.
What?
I thought you said negative 4. Sorry.
I don't think so. But anything's possible.
So the only thing different we're doing is just at the end dividing by the initial.
Yeah. So that's the percent dissociation. And looking at that reaction, percent dissociation is the forward or reverse reaction. Forward is correct. Okay. Now, so that's one thing you want to be comfortable with. You also want to be comfortable with an interpretation. It says for a weak acid, the percent dissociation increases as the acid becomes more dilute. And this is illustrated in your book. I'm going to walk through it slowly, but I want to show you what they give you, and then we'll derive it so that you can see it.
You just replaced that line of text with the number 15.
Look at your,
Click Control Z.
look at, yeah.
Oops.
Look at number 1.
Number 1, 15.
I know, because I hit the keyboard. The book is so heavy. All right. In any event, here's your Ka expression. You're going to have Ka is equal to x squared over the concentration of weak acid. It says, now suppose enough water is added suddenly to dilute the solution by a factor of 10. The new concentrations before any adjustment occurs are. So the new concentration of both the conjugate base and proton or hydronium ion is diluted by a factor of 10. So whatever you started with divided by 10. And the concentration of the weak acid also diluted by a factor of 10, correct? Going back to your Ka expression, you're basically going to use this, and now you've got non-equilibrium conditions because you've done something to perturb the system, and you're going to divide each of them by 10. This 10 and this 10 cancel, correct? Or this and this, it doesn't matter which. And you have x squared over 10 divided by this, or if it's x squared over 10, you just put the divided 10 that's here, right here. And now you have Q is equal to 1/10 Ka. So if Ka is 1, what would Q be? 0.1. So what would be smaller? Q. We said if Ka is 1, Q is 0.1. So Q is less than Ka. If Q is less than Ka, is the forward or reverse reaction favored? Forward reaction. So if the forward reaction is favored, then will the percent ionization increase or decrease? So the forward reaction is favored, you're going to generate more of this, and so the percent dissociation will increase. So when you dilute a weak acid, you get an increase in percent ionization. If you make the acid more concentrated, you would get a decrease in percent ionization, and we'll do that out with numbers as well. It says, since Q is less than Ka, the system must adjust to the right to reach the new equilibrium position. Thus, percent ionization or dissociation increases when the acid is diluted. And let's diagram that out now so you've got it in your notes, because this is really an important concept. It was asked on the 2016, and I've typed something into your notes so you can see exactly how it might be asked and how it might be asked on your mini quiz. So in this particular instance here, again, let's say that you dilute the acid by 10. We had an initial Ka of x squared over the concentration of the acetic acid. In regard to Q, we'd have x over 10, x over 10, concentration over 10, keep in mind that x squared over the concentration is Ka, so this, and this is the Ka, hence 1/10 Ka, and now Q will be less than Ka. The forward reaction is favored, and thus percent ionization increases. If the acid's concentration increases by a factor of 10, you have Ka, but Q now would be 10x, 10x, and concentration of the acid times 10. And here you'd get
That's the bottom of it.
that's the bottom. And maybe able to fly it a little bit here.
Yeah, percent what?
Ionization. What's after favor?
Reaction.
No, after favor.
That's his forward.
And
Oh,
Everyone's hating on her today.
golly.
Dr. K, does it do the same thing if you increase or decrease the concentration of the base?
So now you have Q is equal to 10 times Ka. So now what's greater? So Q is greater than Ka. The reverse reaction and thus percent ionization does what? There you go.
Dr. Taylor?
Yep.
So basically, if it says increases or decreases by a factor of whatever, it's just gonna be the Ka divided or multiplied by that factor?
Yep.
Okay. If like, if this was on like a part 2 question, we have to do the whole
I would.
step thing?
I would. We can take a look at it. It came up, I'm sure it was 2016. I think it was.
Wait, what was his question?
Like if they didn't give us Ka, but they gave us the concentrations and they said this it was diluted by this much, you would have to do the whole thing. Okay.
And we're going to take a look at one.
Wait.
The next problem is slightly twisted, but I feel confident that you can do it. You can calculate Ka from percent dissociation and initial concentration of acid. That's what's shown here. Lactic acid is a waste product that accumulates in muscle tissue during exercise. I'm sure many of you have been doing some sort of physical activity and felt lactic acid build up. It can be very painful. You could be running a race and trying to get over the finish line. In a 0.1 molar aqueous solution, lactic acid is 3.7% dissociated. Calculate the value of Ka for this acid. And that was in your notes already. I threw this part in to make sure you could do it. Give it a shot. And I also want to say that this is about a 5-minute question. Go.
Both parts?
Yep.
Should we go off the sig figs of the concentration or the percentage?
Probably the percent. And again, be sure to answer this piece as well. How'd we do? Are we brilliant? Yes, we are brilliant, but we just need more practice.
So did you?
Yeah.
I see what you did. So for your actual answer, you get 1.36, and you rounded up to 1.4. Solid.
Acids and bases are really fun if you practice.
Why is it 260?
They gave you the percent association in 2, so I got to 2. I didn't even bother.
But you need, because you don't.
On this one, you don't so much need it because it doesn't change anything. You're not working down. You already knew what the X was.
You have to know. I mean,
You don't need it.
It's good to get in the habit.
So 2.7 times 10 to that's theirs because they make it equilibrium. That's the right formula. Do we have to do the Q? Was that asking the question?
Yeah, well, it does. It says explain in terms of Q.
so you want to show it.
Oh, yeah, you're right. How did document it? I still got the right answer.
There's no.
I did the same thing.
That's all I heard from. I just.
What do you care about? It's the same scale, is it?
All right, you're good? Alrighty. That is as far as the mini quiz goes. I had wanted to cover it the other day, but I didn't want to rush through the last part, so I hope that by having the extra couple days, it'll be better for you.
Why is the Q, why is it divided by 20?
Because it said that it was diluted by 20 times.
I didn't see that.
So when you dilute it, you divide it by
Wait,
20.
so then if it increases, what would it say? Like decrease, it says diluted.
It'll say it's more concentrated by 20-fold.
Okay.
It's more concentrated.
Or increased in concentration by a factor of 20. Something along those lines. Or more concentrated. If they don't say what the dilution factor is, make it 10 and do it that way because it'll be easier for you. All right. The next piece we want to talk about a little bit is polyprotic acids. This is in your notes. I really want to simplify this. What does poly mean?
More than
Many.
Many. Like a polygon has more than one side. In any event, with our polyprotic acids consist of diprotic and triprotic acids. Triprotic and diprotic acids as opposed to monoprotic. Monoprotic is what you're more familiar with. For example, chlorous acid, where the acid hydrolyzes, generating the following. Remember, with an acid, you're going to generate hydronium ion. This is a monoprotic acid. It has one ionizable proton. Once you get to here, it can't ionize further. In contrast, with your diprotic acids, you are going to have more than one ionizable proton. For example, sulfurous acid, and then the conjugate base of sulfurous acid can ionize as well. So here you have monoprotic, so you have AKA. Here you have diprotic, so you have Ka1 and Ka2. And you will always find that Ka1 is greater than Ka2. You have what's known as successive ionizations. The first one occurs more readily than the second one. So if you're looking to calculate pH, you really can do it off the first ionization, because not much of this gets made in the beginning and not much of it hydrolyzes. So you can go off the first one. They're not really looking at calculations of this anymore, so we're not going to stress it in any regard. Monoprotic, diprotic. If you had a triprotic, such as phosphoric acid, this is going to undergo an additional ionization. So this is Ka1, and then you'll get Ka2 and Ka3, and this is in your notes. I'm not going to write it out again. But when you're talking about a conjugate acid-base pair, they differ by one proton. Be careful there. That could, be important. So that's just an overview, and again, there would be 3 here. It's in your notes, so it's not worth writing out. It's just penmanship exercise. So monoprotic, for example, hydrochloric or acetic acid. Diprotic would be sulfuric and carbonic. We're going to take a look at sulfuric because that's interesting. It is the only diprotic acid that is strong. Carbonic acid is a weak acid, phosphoric acid, triprotic. So for phosphoric acid, you can see these 3 successive ionizations, and you can see that Ka1 is greater than Ka3. So the first one occurs, and you get some of this, and then this will undergo a second ionization, and then this will undergo an ionization as well. So you have 3. But if you're going to calculate pH, you really can do it off the first ionization, so the first Ka. In regard to the calculation, I don't really think you're going to see much of this anymore. I think we'll just skip it. In regard to triprotic or diprotic, you might see it in the form of a titration curve, and we'll come back and look at that when we talk about it. Carbonic acid, for example, we know is made from carbon dioxide and water, and this acid can undergo 2 successive ionizations. It's very important in regard to hard water and limestone caves, and especially in regard to maintaining blood pH. For those of you who go on to AP Bio, you'll talk a little bit about maintaining blood pH. You don't want blood pH to fall too low because many reactions don't work in an acidic environment, and ultimately you would die because so many biochemical pathways wouldn't function properly. Sulfuric acid, as I said, is unique in that it is the only diprotic acid that is a strong acid. So the first ionization essentially only goes in the forward direction. The Ka is quite large. And while Ka2 is smaller than Ka1, it's still pretty substantial. So while not characterized as a strong acid, it does ionize pretty well. And again, the calculations aren't critical, so we're not going to play there. Make sure you can recognize a diprotic versus a triprotic, and I think if you were asked anything, it'd be asked in regard to a titration curve, and we'll worry about that either at the end of this week or next week when we get into it. We do want to mention that salts can be acidic or basic in nature in some cases. When we think about salts, we tend to think of them as neutral, but the salts that we're most familiar with are neutral. For example, sodium chloride, potassium chloride, the salts that you see in a lot of common food products. There are two ways to determine whether a salt is acidic, basic, or neutral. The first way, the easy way, works great for a multiple choice question, but it's not going to work on a part 2. However, if you had sodium chloride, the cation of the salt comes from a base, and in this case, it's a strong base. So here's the cation from the strong base. The anion of the salt comes from an acid, in this case hydrochloric acid, a strong acid. A strong acid and a strong base generates a neutral salt. Seeing how I did this, what would you predict is the base that reacted with an acid to form potassium chloride? All right, and that is a strong base. And this is the same strong acid. And again, you would predict a neutral salt. In contrast, sometimes you have a strong base reacting with a weak acid or a weak base reacting with a strong acid, and then your salt will not be neutral. The first thing we want to understand is that cations of group 1 and group 2 do not hydrolyze, whereas other metal cations do. So for example, and this is going to fall into a different category, if you had sodium carbonate, what base generated this salt? And that is a strong base. What acid would have generated this? This would be carbonic acid, which is a weak acid. The salt would be acidic or basic? Correct.
So it basically follows the like pH or pOH of the strong whatever acid or base.
Right. So the basic salt would have a pH greater than 7, and that's due to the fact that you have a strong and a weak. So you look at what's strong, and that'll generate.
That'll influence it.
Mm-hmm. And in a part 1 question, multiple choice, you could just do it this way, quick and dirty, done. However, if you are asked to explain why this salt is basic, you have to look at what hydrolyzes. Group 1 or group 2 cations do not hydrolyze. the carbonate ion does hydrolyze, reacts with water to generate bicarbonate ion and hydroxide ion. You are generating hydroxide ion, hence the salt is basic. That's the key right there. Chase, you had a question.
Yeah, so if carbonic acid and sodium hydroxide form sodium carbonate, how would you get sodium bicarbonate? What acid would that be? It would still be carbonic acid.
Yes, it would depend on the concentrations. If the concentrations were the same, then you might only nab one H off, and as a result, you would get sodium bicarbonate. Yes.
Which is still basic.
Yes. It would be based on concentrate. I hate to use the word based. It would be predicted by concentration. So, if when the ion hydrolyzes, it generates hydroxide ion, that's indicative of a basic salt with a pH of more than 7. Make sure you're comfortable with this equation in a part 2 scenario. I'm going to skip down to number 3. I probably should flip my order here because there are some additional examples here. Which ion in potassium nitrite hydrolyzes? Nitrite ion. And it too generates hydroxide ion, hence this salt is basic. So if asked, you can indicate that the nitrite ion hydrolyzes generating hydroxide ion, hence the salt is basic in a part 2 scenario. In contrast, if you have a salt that is generated from a strong acid and a strong base, you're going to get a neutral solution. That's what we've talked about previously. Neither ion will hydrolyze. If, on the other hand, like you see in number 4, you have a salt from a strong acid and a weak base, the salt will be acidic. Let's take a look at that and just put your examples where they match your notes. So this is going to be for number 4. This was for number 2. This is going to be for number 3. So if you have ammonium chloride, again, the base would be ammonium hydroxide. That's a weak base. The acid would be hydrochloric acid. That's strong. Hence the acidic salt. But write a hydrolysis reaction for me. What are you going to react with water? And what are you going to get?
Ammonia.
Yeah.
Ammonium ion?
You get ammonia and ammonia and hydrogen.
So the generation of the hydronium ion is what's indicative of the acidic salt. So what hydrolyzes here is the cation. And this grouping typically is ammonium something. So ammonium nitrate would be another example with the same hydrolysis reaction. So strong forms neutral, strong base weak acid forms basic salt, strong acid weak base forms acidic salt.
What about weak?
So what about weak?
Do you compare the KAs?
Yeah, you compare the Ka with the Kb. If you have a salt formed from a weak acid and a weak base, you compare the Ka and the Kb. If the Ka is greater than the Kb, you would predict the salt is acidic. And that's what's shown here. So with these salts here, and again, you can see they have ammonium in here. If the Ka is greater than the Kb, the salt will be acidic. If the Kb is greater than the Ka, the salt will be basic. And you'll see an example of that in your pre-lab for your next lab.
When you have acetate ion, do you always write the cation after?
No, I'm not so sure why I did it that way. And to be very honest, I probably, you can see it both ways. I typically do this. So here are 3 problems. I've got the answers out, but you could look at it. What strong acid generated ammonium iodide? Hydroiodic acid. So strong acid, and what hydrolyzes is the ammonium ion. Why would this be neutral?
Because nitric acid is a strong acid.
And
Sodium hydroxide is a strong base.
right, and so neither ion is going to hydrolyze. And here's potassium butan, no, bu, 1, 2, 3, 4, butanoate. And again, what's going to hydrolyze is this butanoate ion. So tell me why.
Why did they write it out? Why did you write it out?
I write it out like that because it for 2 reasons. It helps with the drawing, and it reminds me that there's a coup, or there was a coup group in there. Also, if you see an acetate, if you ever see acetic acid is written in this regard, and that's why I write the acetate ion in that regard. And then when you've got, and this is going to get too advanced, we'll do this during the break because you don't need it anymore, it's confusing. Questions in regard to whether a substance is acidic, basic, or neutral if it is a salt. Easy? You understand you have to show the hydrolysis reaction in a part 2 type question. All right, good. Previously. Huh? Previously, we said that Kw is equal to hydronium ion concentration times hydroxide ion concentration. We also said that Kw is equal to Ka times Kb, but we haven't done anything with it. So what we want to be able to do is, if given Ka, we want to be able to find Kb, and vice versa. Very simple. You'll see where you utilize it, exactly what we've done previously, just linking this step in. And that's why the Rice tables and everything else we talked about last time is critically important, because you're going to see more and more of it. This formula right here is provided to you on the back of your periodic table or on your formula sheet. You want to be comfortable with it. Example, it says calculate the pH of a 0.052 molar ammonium chloride solution and the Kb of ammonia is given. If they give you ammonium chloride, tell me why I'm only interested in the ammonium ion.
Hydrochloric acid is strong and ammonium ion is the one that hydrolyzes.
You're looking at the one that hydrolyzes. So tell me also why the concentration of ammonium ion is equal to ammonium chloride concentration. It's a 1-to-1 when you have your dissociation of that salt right there. So here's your reaction. You're starting with a 0.052 molar ammonium ion. You don't know about this. They gave you Kb. Why must you get Ka? What do you generate in that reaction? K. What do you generate in that reaction? Hydronium ion. So is that going to be for a Ka or a Kb? Ka, and that's why you have to first get the Ka. This is going to be critically important in a subsequent section. Once you have your Ka value, then you plug and chug. You get the hydronium ion concentration, which is X. pH is equal to negative log of the hydronium ion concentration. Let's try the example together, and I'll leave you with the problem. Yep.
That's when will they always give you, will they ever give you KW, or is KW always?
That's a constant.
That's
Wait, actually, let me rephrase. Kw is 1 times 10 to the negative 14
Yeah.
at 25 degrees Celsius. If the temperature is altered, Kw can be altered. You'll see a question like that in your practice quiz.
Okay.
But yeah, Kw at a specified temperature is a constant. We're going to do the first example together. Say it again.
Is that given to us or we just know?
Given. Given on the formula sheet. The first example says, what is the molarity? And I'm just going to pen down as we go through. We want to know the concentration of sodium acetate. The pH is 9.10, and the Ka for acetic acid is 1.8 times 10 to the negative 5. What are we going to do? Yep.
Which one?
We would only do 10 to the negative 9.1 to get the.
Well, let's take it through. Let's work a little bit slower. What's your reaction?
Sodium
Acetate ion plus water
generates acetate,
acetic acid. All right. Now, Josh, we have hydroxide ion here, so do we want Ka or Kb?
KB.
Right, and that's what's key. So always write a reaction, because that's going to direct you where you need to go. So Kb is Kw over Ka, and that's going to be 5.6 times 10 to the negative 10.
She already did one.
I'm sorry.
Okay.
Yes, yes? Now we want to know the concentration here. We now have a Kb, and we know Kb is equal to this. And ultimately we want to get this. We have Kb. Can we get these?
from the waste table.
Yeah, you should have the pH.
We have pH. So can we get this and in turn this?
Yeah.
So if we have pH, what do we do?
14 minus 9.
So POH is,
We can't see that.
Hazel.
all right, who said what's going on? Haley, do you see we're making hydroxide ion?
Yes.
Okay. We have pH. Is that going to lead directly to hydroxide ion? No. So we're going to get POH. How do you get POH from pH?
14 minus.
All right. Now we have POH, but we need hydroxide ion. Can we go from POH to hydroxide ion?
Yeah.
How do we do that?
10 to the negative.
But why does it say error?
It's 1.3 times 10 to the negative.
Dr. Claire's from the calculator said error.
From 1
10 to the negative 4.9?
1.26 or I don't know.
10 to the negative.
Yes, I did that. It says error.
Come here. Here, he'll fix it.
You gave me sass. Don't give me sass.
Did you just type the number 10 or did you hit the
Oh,
10?
stop it. You're making a mess.
What the?
Hey. Second clause.
Oh,
Negative.
I
Which is what he was saying, but he was yelling at you, so you
You're
went.
being sassy.
I didn't do
Alrighty.
that. I just typed the number 10.
We have the hydroxide ion concentration. Now can we let it rip?
No.
Yes, we can. This
Why don't you have to find the
is equal to this times this, which is 1.3 times 10 to the negative 5 squared over the KB that we got up here.
About the same thing.
The only piece that's new is you have to go after the KB.
Now, can we rice it up?
We already raised it up.
And as much as I adore all of you, if you have no idea how to do a rice table at this point, you better get busy tonight.
Why are you so excited to raise it up? It's just
Because he likes to say rice it up.
let him.
Would you rather?
Yes, yes?
Wait.
Can you just
Wait, why do you make a rice table?
can you just pause for a second?
I didn't even bother because you didn't need it.
He's asking why you did make a rice table.
Oh, I was thinking we might need it, but then I realized it was a waste of my time.
Okay.
But the reaction's critical.
Like Mr. Morris says,
Wait, don't move it.
if you,
Better to be over-prepared.
if you write empty rice table every day, by the end of your life, you could have wasted like
But it always says like,
He's like,
All right, you have.
on the SATs, you too much work. Good talk.
You have one problem to do.
No, crap.
Actually, I'm going to give you a break first. We are going to take a break. Hopefully, KA, KB, KW linkage is clear. We'll come back, check that problem, and then we have one more piece to do.